I hope, first off, you like the facts. Can I borrow one of those? No, one of the programs. Yeah, look. Awesome, I'll colour match my first slide.
There's a payment for that to speakers who do that.
So, I didn't get to do a picture. I guess the talk is about, I guess it's kind of about how Netflix and Amazon and a bunch of other people kind of build systems these days. I'll come to that in a minute. First off, I guess I'll introduce myself. It's actually my third trip down to Agile on the beach. Anyone been before? A few people in the room. So the first time I was here, I talked about Lego and Star Wars. Awesome. Thank you. The second time, I think I talked about innovation. So this time it's a bit different. It's about architecture. I guess my day job really is, I guess I call myself a coding architect. Maybe that's kind of a good description of what I do day to day. So I spend half my time approximately on projects. There's some people on, in the room actually I'm working with at the moment. And the rest of the time I do things like this, or I do some consulting work around architecture and design and that kind of stuff. So I'm also on this thing called the Technology Advisory Board with ThoughtWorks. We produce a technology radar. There's a bunch of people, Martin Fowler, Neil Fords, that kind of group. And it's kind of interesting. You can go have a look at it. Publish it every 6 months or so. It's kind of about up-and-coming technologies, the stuff that we find exciting and interesting. So, which will break over. So, what am I going to talk about? Well, the first thing, it's funny, it's got this title, microservices. But actually, what I'm going to talk about really are two topics that are kind of quite dear to my heart. The first one is evolutionary architecture. We'll talk a bit about that. We hear a lot about evolutionary architecture in the context of extreme programming and what does it mean to do architecture in an agile world, in a lean world. We heard if people were at Martian's talk earlier, he talked about the opposite of big design up front is not no design up front, it's just enough design up front. Right? That's really what evolutionary architecture is about. The second thing is about emergent design. So where does this idea of design, how does design work on an agile team when you're building out products in an agile way? How do you do design? How do you move away from trying to, avoiding specifying everything up front and giving people the tools, the opportunities to solve problems as they want to solve them, at the same time as retaining some kind of form of control. And I'm going to talk about people and teams, because these things kind of come together to form a sort of what I like to be talking about in terms of the title of the talk, in terms of adaptive architectures and adaptive organizations. So that's really what it's about. I'm also going to put a few other things in. There's going to be, I think, some interesting stuff. There's going to be giants, monoliths, the TARDIS, volcano, turtles, and a cave. So, I guess to start, I have a question. This is where this came from. This came from about 3 years ago. I was at a workshop with Dan North and with Andrea, who's I'm not sure if he's in the room, but he's certainly speaking maybe after this. And one of the themes of this workshop was, or that came from this workshop, was the idea that we're building systems that are just too big, monolithic systems, right? The kind of classic systems where you've got a big old database, big old application, and that's kind of the go-to architecture generally for things like websites and for lots of other products. Now, this is the scene from 2001, by the way, where he's lying in bed and the black monolith appears in his room. That's a server, not very well defined. Yeah, so there's some interesting stats around this. Gartner talk about total cost of ownership of the system. Now, Gartner talk about the fact that 90% of the TCO of the system is actually incurred post-launch. Right? So if you think you're actually spending a lot of money on building a system in the first place, actually that's only going to be 10% of the total cost of that system over a period of time. That's actually small. It's a pretty small amount. It costs you $1 million to build something. It costs you $30,000 to build something. Obviously, you've then got to factor in the additional 90% on top. But often we don't see this because it's often hidden somewhere in a different budget. Say, CapEx might be used to build out an initial product for your, minimal viable products, and then all of a sudden it goes into your big OpEx bucket. And who knows what goes on in the OpEx bucket, right? There's some guy who signs off on it every year, and it's like 10 million this year, and that's pretty much it. But this is a kind of terrifying stat for me, and I think it's related to this idea of building systems that are inherently too big. There's another interesting. We've got any government people in. I think there's lots of government people travelling down. Yeah, we've got some. ThoughtWorks are working quite closely with some of the government departments at the moment. But this is an example of a fiasco in the UK. NHS told to abandon delayed IT project, 12.7 billion. computer systems to create patient research, be scrapped. There's another one that was in the news, I think this week, around, it was in The Guardian this week, around the new universal credit system. They spent hundreds and hundreds of millions on this, and they're now actually looking at, well, I think the quote was, looking at business processes from scratch up again after a couple of years. So this is terrifying. This is real. This is real money, and in the case of things like the NHS and universal credit, it's actually our money. For the UK taxpayer, we're paying for this. We're paying for this. So this is the other thing, right? We have to rewrite then these systems every couple of years. That kind of sucks. Any CXOs in the room? There's sort of CTOs or that sort of group. We've got one at the front who's daring enough to admit that we're in this position. Do you like this? That we have to rewrite these systems every couple of years? Is that a good thing? Yeah,
it's too complicated.
Does it make you happy? Because I don't think it makes many people happy. We've got this 2 to 5 year change cycle where effectively we would have to rewrite, right, a solution that has become too difficult, too big, too hard to maintain after a relatively short period of time, incurring massive cost in the process. So I quite like the idea of telling stories. I tell stories a lot to kind of illustrate my points. So I'm going to sprinkle some through. The idea of being a storyteller is quite nice. There's a guy, Simon Stewart, who I used to work with, and he has this idea of a team Shaymin. So the team Shaymin is the person who can tell you the story of how things got that way. Right? So you start a new project, you start a new job, you look at a new team, you look at this awful build file, and you're like, this is XML, it's like 1,000 lines of XML. This is terrible. And you start talking to the rest of the team, this is terrible. How could you possibly have written this? And the team Shaymin gathers you together and he says, let me tell you the story of the Right. So stories are powerful. Stories are quite powerful. So I'm going to be a bit of a Shaymin about some of my experiences at various organisations when I've been doing sort of architecture consulting. And they're generally quite scary, these stories. And the first one involves, as I say, this sort of monolithic system. It was an airline. I was visiting an airline. I was there for about 3 weeks. We were asked to have a look at their architecture and their systems estate and provide some advice for them on how to get themselves out of the mess they were in. It was a fairly standard topology if you're into your kind of database integration. You had a retail site and you had some departure control systems talking to a database. .NET shops is single server. This is pretty much the business of airlines. You've got inventory, which you need to sell, which are effectively bums on seats, and then you've got getting those bums through departure onto the planes. That's effectively the systems you need to run an airline. Obviously, there's all that kind of stuff as well. Now, the story of this system was they built this. Originally, they built a departure control system in the database, and then they thought, right, we need to sell this stuff online. Online's the way forward. So we'll build a retail site and it'll talk to this database. And these entirely separate deployed applications talking to the same database. And then they grew, and then they grew, and then they grew, and then they grew, and suddenly they had this enormous database, which they were having to replace every sort of 12 to 18 months, right? Now these boxes, 48 cores, quarter of a gig of RAM, about $1 million per box, and of course they're sensible people. They don't run one of these. That would be nuts. It's their organisation that's relying on it. So they've got 4 of these, or so, active, passive, across 2 data centres. This is interesting. NUMA, non-uniform memory access, it actually meant that single server version they were running couldn't even run properly on this because it couldn't take advantage of the NUMA setup. That's, I guess, by the by. But they ended up with this enormous database, which every 18 months was costing them about £4 million just for hardware replacement. Right? That's quite sucky. If anyone knows the story of Amazon, on how Amazon Web Services actually got started, it was this. This is what happened to Amazon. So they ended up with their retail sites talking to a massive database. They grew and grew and grew and grew. Their database got bigger and bigger and bigger, until eventually Bezos said, as literally a diktat, no more, we're not doing this anymore. We're actually going to move to a service-oriented architecture, and anyone who doesn't, we're going to fire them. And that's literally the kind of diktat that came down from the CEO of Amazon. Now, this is basically what you do. You're just burning cash at this point, right? £4 million dollars every 18 months, just on hardware alone. So of course, being a good consultant, I went away and wrote a 40-page report to explain exactly what was wrong with this, and I used language like tightly coupled, golden hammer, single point of failure, all these kind of things that you'd expect to read in a report on your systems. The consequences are expensive to scale, high operational cost, high cost of failure. Brilliant. Right? That's tick, tick. I've done that. You know, as a true architect, I've solved their problem for them. The thing is, I mean, this is all very well, right? And it's actually true. This is technically what the problem with the system were. But actually, they were kind of never so well sort of demonstrated when a volcano went off in Iceland. You might remember this a few years ago, and it grounded lots of flights. It was a big disaster. And the interesting thing with all these kind of technical, these jargon phrases, you know, tightly coupled, operational cost, all these kinds of things. In the real world, in business terms, this had a massive impact when this volcano went off. And the reason is because, well, maybe you can help with this, right? So, volcano goes off, you're worried about your flight. You've got a flight booked with an airline. What do you do? What's the first thing you do? Use the website. And lots of people, many more people than usual, go to the website. So the database load goes, and consequently the website gets slower. Now, what do you do when the web page you're looking at is slow to load? Yeah. So you press F5, and then the database goes, oh, no, I'm just and just blew up, went away. And actually, the problem is they could actually fly. Their planes were capable of flying. But this thing couldn't talk to the database. Right? They couldn't physically get people through the gates onto planes. They had to revert to paper. Right? That was the actual operational cost. Huge reputational damage, because even though they had planes that were capable of flying their routes, they couldn't get the inventory of people onto those planes because of tight coupling and kind of interesting. So here's my cave, Plato's cave. I talked about architects, architecture, solving real world problems. I'm going to talk through some examples, what I mean by microservices, and I'm going to use a sort of an example product. And in Plato's cave, people know who Plato was, the philosopher. Plato's cave was described as you have a group of prisoners tied up hand and foot, and they're kind of staring at a wall, and behind them is a fire, and people pass objects in front of the fire, and they see the shadows on the wall of the object. Plato's point was, is there a platonic form? Is there a real form of if you hold a banana up, does the shadow of the banana equal the real banana? Now, I guess what I'm saying is this does not equal the real architecture. It's slightly more complex. But this is the shadow on the wall of the architecture, effectively. And this is a kind of, you can think of this as a sort of investment bank in a box, or retail bank in a box. It's got some user management, rules, reporting, access to entitlements, analytics, call center, and a bank account. Pretty straightforward. It's what you would do. What we did do when faced with the opportunity, the challenge of building a product. Now, the sort of traditional way would be to get everything together, big database, right? Maybe use something like Spring. You get Spring and Maven together, and then they bring all their friends from the internet. This is awesome. And you can put everything into the same boxes. It's fine, right? But looking at the lessons from people like Amazon, people like Netflix, back 2 years ago now, we thought maybe there's a better way of doing this. Because effectively, what you have in domain-driven design terms are a whole number of different bounded contexts. In this case, operating within the same application, right? The same big application, lots of different bounded contexts. So we thought, wouldn't it be useful, maybe interesting, if we actually split these contexts off, and we had separate applications or separate bounded contexts, or business capabilities in this case, instead of the one big application. And crucially, we moved the data as well. So we didn't just have a big database, lots of applications talking to the same database, we actually moved the data out as well. So bounded contexts owning their own data, and where necessary, duplication of data between the two. That's the first thing, really, is this idea of hexagonal business capabilities, right, which own their own data, which look like this. So separate, completely separate bounded contexts. Nice animation. Did a magic move. When I found magic move in Keynote, it changed my life. Awesome. Yeah. So in our world, what we had is all these different boxes, which were, generally were going to be put into one big application. So I'd like to split them off into separate bounded contexts. This might sound familiar if people are aware of the discipline of service-oriented architecture. because this is where this stuff came from. And this is where really the giants part of this comes from, is that a lot of this is not new, a lot of this is standing on the shoulders of giants that's doing all of it together. So, business capabilities, and one single one of them, which is the user capability in this case, was then separated out into a number of small, tiny applications, each doing a specific job within it. So that business capability was decomposed. We actually had two databases. We had an event store, we had a user store, we had an event queue fronting the capability, we had some event processors, and we had our user service, which was the system, the source of truth for data about users in this system, in this product. Incidentally, this is open group. Archimate 2, from the people who brought you TOGAF and MODAF, as architects in the room, that is the correct diagrammatic notation for improving my chops. Yeah. Well, that's all very well. We've got these things separated out. We've got small applications. That's no good if they can't talk to one another. This is where most, I think, service-oriented implementations fail, is they don't standardize on some mechanism for talking to one another, right? And the key thing with this is that these capabilities should share a uniform interface. So what does that mean? Well, in our world, each edge in of this hexagon shared a uniform interface with every other one, and with all the other capabilities. We chose a standard protocol for these things to talk to one another. This is from some work that Alistair Coburn did, a famous dude from the Agile world, the Evolutionary Architecture world. This is called the ports and adapters pattern, or hexagonal architecture. You can go and have a look. He sort of talks about it in the context of UI, and how to improve testability of UIs. But it's really, really useful to metaphor in this case. So that's cool. Right, we're going to choose uniform interface. What are we going to choose? What we did is, well, I don't know, what do you reckon? Oh, damn, jumped right to the end of the story. Well, I said what we didn't do, and this is time for another scary story. What we didn't do is this. Right, so this is a real diagram which has been suitably anonymized. This is known as the rainbow diagram amongst certain of my colleagues. The different colours represent different types of data. So you've got green over here, that's say users, in green up here. Effectively it's separated out everywhere, so very, very different. And this is kind of an example of something called, oh yeah, this is my favourite bit. Why have middleware, like an enterprise service bus or something, when you can have a middleware database? This is pretty awesome. Yeah, so we have this kind of middleware database. Basically lots of direct database-to-database integration going on, ETL and so forth. And this is an example of something called the stovepipe enterprise. This is described as systems procured and developed to solve a specific problem characterized by limited focus and functionality, containing data that cannot be easily shared with other systems. That's from 1999. Standing on the shoulders of giants again, right? This is not something that's new. We've known that this is kind of a bad idea, potentially, for decades. And most actually organizations, this is, if you're in a big company, a big enterprise, this is probably the least of your worries. It probably looks a bit more like, I guess, kind of like this, right? This is what most big organizations do. You go to a big bank, you go to a big insurer, it's incredibly complex, the kind of systems they can find. And of course, you go to one of these organizations, and again, you write your architectural report, and you say things like, logic scattered everywhere, data scattered everywhere, and it's difficult to predict the effect of change, which system is right, and BI, MI almost impossible to get at. Where do you go to get this data? If you change something, you have to change it in multiple places. All very, very hard to reason about, hard to maintain. So we could do that. We could, for our capability, we could all just talk to a giant middleware database, say. But we thought, jumping ahead in the story, maybe we won't do that, and we use something called RESTful integration instead. Now, again, looking at the date, this is 2008, that this presentation was done by a guy called Leonard Richardson, which is a long time ago now, a relatively long time ago in computer science terms. Justice will take us millions of intricate moves. And he's talking about why do we start, as enterprisey people, do we have to invent stuff all the time? Why do we have this not invented here syndrome? So we'll just, we need to talk system to system, distributed system to distributed system. Let's invent something called SOAP or CORBA or RMI or all these different things, all right? All these different things that we've been doing for a long time that we just invent. His point is actually there's something out there that's quite a big distributed system, and it might work for integration problems as well. And that thing is the web, right? He talks about the web. And he comes up with this maturity heuristic for the web, where you've got plain old XML at the bottom, resources, so the representation of data as resources, and representations of resources. But level 2 is using HTTP verbs, so all the verbs from the HTTP protocol rather than just tunneling over a single one. And then he talks about hypermedia controls as the glory of REST. So hypermedia, which in itself is an entire presentation, but the use of hypermedia and embedding hypermedia controls within resource representations gives us the ability to decouple the parts of our distributed system from one another, enabling us to change them independently over time. Yeah, and I put this in because it's my favorite animation ever. Behold, the twin fists of hypermedia as the engine of application state. And so when you get to level 3, you're able to use this idea of hypermedia controls to decouple the different capabilities from one another. So what does it mean in our case? Well, in our case, what it looked like is something like, I guess, this, right? We had, so this is a HTML representation. In here we've got a form, we've got some, which allows us to update users. We've got an index where we can go and get all the things we can do with users. We've got some a link to itself, so you can refer to itself. The cool thing about the form is that actually it's got default values in there. So if you go to get information about a user, you automatically have the ability to edit the user by submitting the form, which is quite cool. So in our case, as I say, we ended up using HTTP as our protocol, and we ended up using the web as our uniform interface, effectively. And so we had things like user requests, and then an individual user request was user request 123 as the standard interface around our business capability, composed of microservices or micro applications. As you can see in that, there's 3 of these little applications. Now, how big were they? Well, I'll come to that in a minute. You're probably familiar with the kind of turtles things just from Terry Pratchett's Discworld. And in the Discworld, the answer to the turtles all the way down question is it's turtles all the way down until you hit the elephants. Right? Whereas, which is kind of how I see this, it's turtles all the way down. How small? Turtles all the way down until you effectively hit assembler, until you hit jump at the bottom. We should be talking about things that are smaller with a single responsibility. And the single responsibility piece of this is the absolute key piece. So what does that mean? Well, yeah, this is the Plato's Cave version, and actually, I guess it looked a bit more like 3 applications and 2 different databases. What I mean is, as you dive down, as you chunk down the levels of domain, technical domain abstraction within this, you should have a single responsibility. So as you go down into one of these applications, you have objects, which we all know, solid principles, should have a single responsibility. And when you get down to the level of an object, that, as I said, should do one thing. And this is my conjecture. This came up in a project I was on with Dan North, who was in the keynote earlier, that my measure of single responsibility, rather than being size of, or anything kind of abstract like that, it's if I put my head up against the monitor, is it bigger than the size of my head? If it is, it's probably got more than one responsibility. You should probably split that out. So that's my conjecture. That's fine, because I've got quite a big head, not a lot in it. So it's actually fine. But this is about turtles, as I said. It's about turtles all the way down and then all the way back up again. So you have object with single responsibility. Likewise, you have components with single responsibilities. And then you have, as you chunk up, you have capabilities with single responsibilities and products with single responsibilities until you reach the top. So, as I say, as we chunk up these levels of abstraction, each of those conceptual levels should fit into my head in its entirety. Right? They should have a single responsibility. And in this case, it was about hundreds of lines. It was like, I think the biggest was about 700 lines of code. And these were doing things, so we had an event queue, which was the responsibility of that was simply to be the transactional boundary of the system. The event processor, single responsibility. It read stuff off the queue and created users. User service, single responsibility. It was the system of record for users. So single responsibilities all the way down. And as you chunk up to that capability, it had a single responsibility, which was to manage the users. That was its single responsibility. You can understand this. At this point, a lot of people start to talk about reuse, and I've got a word about that, which is don't reuse stuff. You can reuse stuff at the level of services, and obviously, We use stuff at the level of infrastructure, but you get into all sorts of problems when you start to do things like share domain code around. So that's just an idea there, is not to share domain code, domain logic, rewrite it. Netflix are really good at doing this. Now this looks like the weirdest page of film titles that you've ever seen. Just carry on. Actually, this is the Netflix open source page. If you go there, they've open sourced all of their infrastructure code that they use. So all the stuff they've created to make things easier for their own developers, they've open sourced so other people can use them. So it's things like starting up instances in the cloud, or managing Cassandra instances, or creating small services. All this stuff they obviously reuse across all their teams. And they've got about over 300 services, I think, running. 300 of these small applications deployed, I guess, like 15 different boxes and scaled massively. But all that stuff that they wrote to make their lives easier, they've now open source. So they're reusing at the level of infrastructure and at the level of technology underneath, not at the level of the domain. So the next thing is we've still got this idea of standard protocols. The problem with standard protocol, in our ideal world, we've got totally decoupled clients and servers, which hypermedia helps us to do, but only to a certain extent. Now, there's a philosopher in Noam Chomsky. He uses this example of, well, yeah, he didn't use time laws like an artist, but he uses the example: time flies like an arrow, and fruit flies like a banana, to identify the difficulty that computers have in understanding language, right? Understanding programs. There's a massive what's called the semantic gap between what we're able to do as humans when we're looking at a website, say, and what a software agent that we've programmed can also do. It cannot identify the difference between, it's very difficult rather, to work out what the difference in semantics are between these two statements, even though structurally they're identical. Very, very hard. What does that mean? Well, what that kind of means is that if you end up in a situation where you've got multiple ways of doing the same thing between services talking to one another, this is one issue that SOAP had initially. You could write any number of methods in your WSDL. Which one do you choose? But you can have many different ways of doing the same thing. And if you're a software agent, how do you choose the right one to use? That's what this idea of a semantic gap is. It characterizes the difference between two descriptions of an object by different linguistic representations for instance, languages, or symbols. So as an example of this, if you want to create a user, on one end I could be saying I want to register one, and on the other end I want to say I want to create one. What do you use? How do you program an agent, some kind of system, or some client, to know intrinsically which one to use? That's okay, because you can actually use things like standard application protocols and domain protocols to kind of close this gap slightly. It doesn't go away entirely, but you can provide a common set of operations that clients of your services can actually use to interact with those services. Everyone obviously is familiar with that RFC, so I don't need to go into it much. And does anyone know what that is? It's Atom, thank you. Yeah, it's Atom Pub, actually, that one. There's a great book called Wrestling Practice, which talks in great depth about Atom and Atom Pub. But Atom Pub is, we use this, Atom we use generally, or we're exposed to in terms of feeds and feeding it and things, right? But you can actually use it. You can use it in a way that's kind of maybe unfamiliar. You can actually use it as a kind of standard protocol to allow us to get systems to talk to one another. So what does that mean? Well, Atom with Atom Pub is quite simple. It's just a set of resource representations that are described in the RFC that you can program against. Right? Your browser or feed reader can program against it, but also, likewise, clients can use it and program against it to talk to other systems. So you have workspaces composed of collections, composed of entries, and they're composed of user types. If you like, it's the envelope. It's the envelope and the set of things you can do with that envelope as well in one RFC. So that means, rather than having two different ways, register and create, you have one single way to do this stuff. You have post to users and post to users. And you can just post the same thing, which is an entry in Atom terms, to an endpoint, and you'll get the same result. So that's what we did. we decided on using a standard MIME type. We decided to use standard, the RFC, to allow services to talk to one another, to close the gap. So in this case, user request was an atom collection, and user request 1, 2, 3 were entries. Everything clear as mud, right? It's not like I'm covering a lot of ground. So the next thing is this idea of independently scalable and deployable. I really like the description of architecture, or the job of architecture is to give you flex, is to give you degrees of freedom. Right? A well-designed, well-architected system should allow you to flex in multiple different ways, either by scaling out number of instances of something for throughput or availability or for reliability, or to be able to maintain them more easily, all these different things. This is not my idea, I can't remember, I'm afraid, the reference, but you can probably look it up, degrees of freedom in architecture. But this is a really nice description of really what the job of an architecture is to provide degrees of freedom. So here's an example of a system that I don't think does that, which is another client I was at. In this case, what we have is a number of products, again, all in the same place. Lots and lots and lots of products, all in the kind of same place. All talking to one big database. This is slightly simplified. And the problem with this is we have, say, I don't know, we have, if it was an investment bank, we might have sort of capital markets over here, we might have kind of volume trading in the middle, we might have different types of products all in the same place. Now, these things have different characteristics, right? You want to be able to flex these things in different ways. So as an example, one part of your product might have a small number of users, or relatively. One part might have a tiny number of users. One part might be much more used by your users, might need completely different scaling characteristics for throughput. If you've got everything in one place, what are you doing? Well, effectively, rather than being able to deploy and do stuff on different sized boxes, maybe minimizing the operational cost of this kind of system, what you're actually doing is insisting that you have to put everything in one place. You have to scale to the lowest common denominator, or highest common denominator in this case. But there's another thing, right? Different parts of your product might change at different rates. One part might be being incredibly actively developed by one team. There might be another part of your product that is kind of fairly stable, but occasionally needs small changes. Depending on release cycles and things, you're effectively tying the different products, change cycles and release cycles together when they're all in one place. This kind of sucks. This is an example of what sucks. This is something called a value stream map. Effectively, the top bit is value adding time, the bottom bit is what's called wait time. So this is when we're actually doing stuff that's useful, say it's writing code. This is when we're doing stuff like waiting for handovers, right? Waiting for releases. This is a real one, and this, as you can see, the value adding time was to change something on one part of one product on one site. There was actually like a 30-day wait in the middle because this client was one part of the product was reliant on the change cycle of a different part and couldn't be released until the other product was ready to be released. Now, if you're a business person in that case, you ask the developer, how long is it going to take to build that? And they say, well, it's about 3 days, it's pretty straightforward. Okay, well, when can I have it? I don't know, 6 weeks? What? What is it? Are you insane? Again, it's a real problem. Real problem. So back to our Platonic architecture, Plato's cave. What does this mean when we split this up then? When we've got different capabilities, when we're separating, say, products out, separating bounded context out? Well, it gives us more degrees of freedom in our architecture, essentially. We're able to do things like deploy one of these things on an individual box. That's kind of cool. We might have 3 boxes. We might put one on each one, depending on the cross-functional characteristics of those services. Well, we might do something different, right? We might say, actually, we need more. We'll have 3 processes running on one box. Or we might say, we'll have 3 processes running on one, and the other 2 services, we'll deploy them on the same box. You've got options suddenly. You're not just doing one thing. You're not just putting one big box, one big application full of all these products into one place. Plus, you get to change them independently from one another. And that's, again, very powerful. So which brings me to right tool for the job. I'm hoping, maybe I should have changed this and said use the right spoon for the job, I guess. But I'm hoping every talk will have the hammer in it. Because so far I've been to 2, so that's good. They've both had hammers in. But use the right tool for the job. What does that mean if you've got 10 minutes, thanks. If you've got lots of these independently deployable things, independently changeable things, right, you're no longer constrained by having to use the same tool to build everything in one box. You can flex and use different tools depending on the different characteristics of each of these individual capabilities. So as an example, this is kind of a current example actually, it's the client I'm working with at the moment. I won't embarrass people in the room who are working there, but they're fantastic. If you see me later, I'll tell you who they are, because they are awesome. So in this case, we've got maybe three different capabilities. We've got, say, a product, we've got some user management, and then off to the side, we've got some monitoring. It's an event-sourced application. So we've got kind of real-time streams or near real-time streams of events coming out. Now, yeah, you could use C# to do that, but actually you can do some really cool stuff with Node and put some stuff on top of Node, and suddenly you've got a nice kind of real-time monitoring solution. But the cool thing is, we're able to do that. We're not all in one place. We can choose different tools based on the different capabilities, different cross-functional and functional requirements of the application itself, of the product itself. Another example might be, we can choose to use different databases in different places, right? Our production store might be Mongo for various reasons, but our data warehouse, we might want to be using SQL Server to do our data warehousing, say. We then have this idea that Dan North has talked a lot about. He didn't talk about it today. He's talked about it in other talks, which is the idea of being able to easily replace parts of your application. Not maintaining it over time, but replacing it. If you've got small applications, tiny applications, right, adding a new feature to one of these applications, it might actually be easier to rewrite the entire thing if it's 500 lines of code or 300 lines of code, rather than add a new feature into something that's already existing. You could just throw it away. Throw it away and start again. The actual sunk cost there isn't that great. Right? So this might look like this. We might choose over time that our reporting requirements are better served by a different type of database. Obviously, we're all NoSQL experts in the room. We love the graphs and the document stores and so on. There's maybe a serious case that we could model this particular set of data better in a graph than we could in a relational database. So we'll migrate to using a graph store. Well, that's kind of okay, because you can kind of do that with this kind of model. You've got these hexagons, ports and adapters. We'll just put on the side another small application back on Node. And when that's ready, we'll time that. Finally, I guess I'm going to talk about this idea of auto-scaling and status aware. Now, this is something that is characteristic of pretty much all of the projects I know that are using this kind of architecture, bar the one I'm on at the moment. Netflix, AWS, so Amazon, all those guys and many others are all. And in fact, we did a survey internally of I think 60% of our current projects are using this form of architecture at the moment, and I think 80% of those are actually doing infrastructure automation so that everything is automatically scaled and is kind of status aware. What does that mean? Well, there are lots of tools now to allow you to, rather than have, we'll build one box and then that's it for our application, we'll buy another one, and we'll buy another one if we need to. If you go out to the cloud, infrastructure as a service providers, Heroku, etc., or EC2, Rackspace, then they allow you to automatically scale up and down your hardware in response to demand. Right? So, say we've got a typical kind of, you're a UK-focused website, your demand is probably going to go like this. During midday at lunchtime, you're going to have a high period of demand. At night, not so much. You avoid the fact that you've got a provision for the highest demand the whole time, with probably some overhead, and you allow yourself to kind of track by turning boxes on and off automatically as your demand needs change. And that's a really exciting kind of idea that you can use when you're starting to use architectures with more flex in them, more services, different capabilities. Status aware is the idea that applications should know themselves how they're doing. So this is related to the kind of reliability aspects of systems. In our example, the event processor was able to the event queue exposed its own queue depth as in its status. So it would say I've got like 100 messages, 1,000 messages backed up in my queue. you can do stuff in response to that. Start new processes to drain the queue faster, right? Or potentially other stuff. I'll just go through this story quite quickly because it's my favourite story. So the zombie apocalypse was an organisation in Australia who are using Amazon to scale, using Amazon, sorry, for their development and testing environments. And they had this idea that over time they've used about 700 machines, I think, on them, pretty much every day. And when they start these machines up, they tag them to say they're part of the UAT environment or acceptance test environment or whatever. But the problem is sometimes the tagging fails. The API call doesn't result in the tags being applied. So they end up with these things they call zombies. Zombie machines just running in the cloud randomly. And they don't know what they are, they don't know what they do. So they're, oh, this kind of sucks. So they wrote something called the zombie killer, which is, the zombie killer, which was also running in EC2. And that would just overnight walk through all the untagged instances. This is perils of automation, maybe this story. Walk through all the untagged interfaces and just kill them. That's fine. And in the morning, if they needed more, they'd start more. And then one morning they came in, and they thought, that's funny, we had 700 of them running last night. I think we've lost 60 overnight or something. That's kind of strange. What's going on? Well, they investigated, couldn't find anything. The next morning they came in, they only had 10 or 12 left. So they, pretty much including all their continuous delivery, build servers, everything had gone overnight. And they worked out that there was a bug in the Ruby API for Amazon. So when you asked for all the untagged interface instances, it gave you back everything, all of your boxes you had running. And because the zombie killer was on Amazon itself, it just got this list of every machine, walked down it until it found itself, terminated itself. So the first night, it would happen to be up here. The second night it was down here. And they called it the zombie apocalypse. So obviously, if you can avoid that, that would be good. There are some dangers when you do this kind of stuff, but I just like that because it's a fun story. Teams. I have to walk through this very quickly. You can organise teams around these as well, right? You can organise product teams around individual capabilities. Usually, we look like this: business, PMO, ops, testers, developers, with this kind of yawning gap, yawning crevasse of doom. I think Dan called it. In the middle. And actually what you can do is you can create cross-functional teams around these capabilities. This is what Amazon famously did with the 2 pizza teams. Teams big enough to be fed by 2 pizzas, formed around their individual services. The Amazon website, the Amazon homepage, is set for about 200 services or something crazy. Now I'm not saying have one team for each of those, maybe one team manages more than, or several of these services. But forming teams around these boundaries is an interesting approach. And it's related to this idea from Melvin Conway's law, that if you do this, you can actually reinforce the structure of your designs. You can reinforce the kind of architectural boundaries of your capabilities. Organizations which design systems are constrained. Effectively, what it says is, if you've got a team of DBAs, a team of web devs, and a team of Java middleware people, you'll end up with a website, some Java middleware, and a database. That's basically what it says. Or if you ask 9 people to write a compiler, get a 9-pass compiler. So you can actually organise teams around these things, organise teams around products. This is, again, not new, we're standing on the shoulders of giants. And this is, in that case, in that product, we did that. We had small teams, 3 pairs maximum, working on multiple capabilities. So I sort of said, something about sort of adaptive architecture, providing flex. This is kind of fine-grained SOA, Netflix call it. It's SOA++, SOA done right. It's been called a lot of different things. When you layer a lot of these things on top of one another, I think you get something that's kind of exciting, especially now with infrastructure as a service. You can making things like auto-scaling, automated deployment, automated provisioning, all these things are much, much easier for us. Right? There's other books out there, go and read these, they're awesome, but it's basically building on a bunch of this stuff. It's domain-driven design, it's REST, it's RESTful integration, it's the releasing stuff like Nigel did about reliability, and it's obviously based on continuous delivery. I guess I'll wrap up by talking about the Unix philosophy. Now the Unix philosophy, this is from the original Lion's commentary on Linux, or Unix, sorry, which is the original text describing what happened when Unix was born. Right? And the author's talking about when the pipes and filters metaphor first arrived. Right? So files are the underlying metaphor for everything in Unix, if you come across this idea. And he sort of says, the next one we had this orgy of one-liners. Everyone had a one-liner. Look at this, look at that. Everyone started putting forth the Unix philosophy. Write programs that do one thing and do it well. That's a single responsibility principle. Turns out Bob Martin didn't invent that at all. Turns out it's been around for quite a while, the single responsibility principle. Write programs that work together. Write programs that handle text streams, because that's a universal interface. At the bottom, with pipes, many programs could work together, and they could work together at a distance. This has been around for quite a while, standing on the shoulders of giants indeed. And if you replace pipes with HTTP, it makes even more sense. So, consistent and reinforcing practices, hexagonal business capabilities. There's the idea of these micro-applications, microservices within them, small hundreds of thousands, whatever line of code that talk to one another, which you can then rewrite if you don't want to maintain them, get rid of them and write a new version. Right? And this idea of a distributed bounded context across them, these capabilities. Deployed, and this is the more technical aspects of this, as containerless OS services with standardized protocols and auto-scaling and designed for failure from the ground up. On a brief note, this is all about trade-offs, right? If you're building systems, it's all about trading stuff off. Effectively, you're trading off how much is it going to cost to buy lots of big boxes versus how many users can I support. You're trading off, how portable do I want this thing to be versus what's the cost of developing the application to be portable. You're trading off, how replaceable is this versus how maintainable is it? Do I need to replace it? Can I maintain it over time? Right. And these kind of ideas, which evolutionary architecture, which is the kind of the bit in the gaps, if you like, it's the bit that puts the flex in. It's the just enough architecture up front to allow you to zone these applications. And emergent design, which is allowing your teams to work within those zones, within the capabilities, to choose the right tools, to organize in the right way, to organize in their own way, right? That actually helps a lot with this. And that, I think, is just about on time. Well, I don't have time for questions. Hooray! But I'm going to be around the rest of the conference, so please, thank you, and I'll see you.